Yeah, thank you for giving me this opportunity to present the work I've done during my PhD at UQAM in Montreal, in Canada. This work has been supervised by Julie Thériault in our research group. And during my PhD, I had the chance to participate in different field campaigns. And I wanted to start with this picture here because this is an example of field work I've done during the COVID. So I was supposed to bring this MR2 here to New Brunswick where we had a field campaign, but I was stuck on the other side of the border because border were closed during that period, and I had to install the MR in the parking lot in front of my motel room where I documented the storms. And that was an interesting adventure during COVID. When we kept doing our field work. So in our research group, we're interested in better predicting winter precipitation types that have all their own impacts and hazards. So most important of them are freezing rain, ice pellets, snow, and wet snow. And here a paper by Kunkel in 2013 showed that ice, so freezing rain, is one of the precipitation types on which we have the less knowledge. So it motivates our work to improve its forecast because it accumulates on branches and can cause a lot of damage. And we had a big example of this last April in Montreal. So that was a really surprising freezing rain storm event. So we were expecting a bit less than 10 millimeters of rain in Montreal, but instead we received more than 30 because the temperature remained constant at around -2 degrees at the surface during that day. And the forecasts were predicting that it would go a bit up, a bit above 0 degrees, and that it would turn into rain, but instead we received this 1 centimeter of ice accretion. So this is a picture of a post on the rooftop of our university showing this accretion. So during that crazy storm, 1 million people in Montreal lost power for more than 24 hours, and a lot of people still had no electricity 7 days later. So it was a really important event in Montreal. So here are a few pictures. So this is my car here, and behind is the car of my friend. So it shows the wrong place to park his car before the storm. And yeah, all the streets look like this. So it reminded us of the importance of better predicting this type of precipitation. And it will change with climate change as well. And this is 2 weeks later, parks in Montreal still look like this. So people even built small houses with branches. So these different precipitation types, they normally form when a warm layer forms above a cold layer that is near the surface. So this is often associated with a warm front passing over a region. So snow aloft would melt at different degrees and then refreeze or do not refreeze to form freezing rain at the surface. If the melting is almost complete, what's remaining of ice in the raindrops would initiate the refreezing into ice pellets. And if the melting is more light, then the snowflakes might not collapse on itself and will observe refrozen wet snow at the surface. Also, if melting is complete, there are still ways that the raindrops could refreeze before reaching the ground. And these are not necessarily well studied, and a lot of my PhD was to understand the different formation processes that can lead to ice pellets when the snow particles are completely melted. So first hypothesis for the formation of ice pellet in case of complete melting is immersion freezing with primary ice nucleation particles that would be already in the supercooled raindrops. However, we know that at temperature above -degrees, when we normally observe these this type of ice pellet, well, the concentration of INP in the atmosphere is very low and cannot really explain all the ice pellet occurrence that we have at this temperature. So in most microphysical schemes, rain can freeze in the model by this parameterization done by Big in 1953. So I've plotted this parameterization here, and what we see is that it is the fraction of total raindrops that will refreeze after falling on 1,000 meters at different temperature. And for big raindrops of 5 millimeters, for example, at -6 degrees, less than 2% of total raindrops would refreeze if we use this parameterization. So another explanation for ice pellets forming from completely melted snow is contact freezing with ice crystals. So ice crystals have often been observed together with raindrops. So that's from Newfoundland field campaign in the 90s. So we see that there are needles that are together with ice pellets on photographs. And the presence of these ice crystals is explained by possibly the secondary ice production from the fragmentation of freezing drops or from Hallett-Mossop process if these ice pellets rime in the sub-freezing layer. And now, how can ice crystals explain ice pellet origin and ice pellet explain ice crystal origin is still to be understood. So because of our lack of knowledge of ice pellet formation process, operational forecasts use diagnostic algorithm to predict freezing rain and ice pellets. So these algorithm works by quantifying at each grid points in the model the melting energy, refreezing energy, and using different observation of freezing rain and ice pellet to do the forecast. So for example, if you have low refreezing energy, you mostly will observe freezing rain at the surface. If you have high refreezing energy, you will mostly observe ice pellets. However, this method ignores the three-dimensional distribution of precipitation particles, which can lead in errors. And it's known that this method is not really successful in well predicting freezing rain and ice pellets. It's also difficult to predict well ice pellets because they are not observed well. First, it's a rare precipitation types as freezing rain, and also they are not reported automatically at automated weather stations. And what explains this partly is that ice pellets have very similar characteristics as raindrops, so their size distribution is quite close and their fall speed is really close as well. However, ice pellets can be well detected by remote sensing instruments because the refractive index of frozen drops is lower than raindrops. So there's a difference in reflectivity measured by radar of about 7 dB. Moreover, there's a differential reflectivity local maximum that has been associated with ice pellet refreezing. Sorry. So all these gaps in the literature led to 3 research questions for my PhD. The first one was, can a laser optical desometer, the instrument that you see here, an instrument that is used by many research groups and in many field campaigns, can it automatically detect ice pellets, and can it inform us on the process, the microphysical process that led to the formation of these particles? Second, what is the process leading to freezing rain when the snow is completely melted all of? And finally, if we identify this process here, can we implement it in atmospheric models to improve the representation of freezing rain and ice pellet? So to start the work, we've done some field work. So we were able during two consecutive winters, to identify and document 4 ice pellet and freezing rain events at a rooftop station in downtown Montreal. So during these events, we do manual observation at every 10 minutes. So we identify precipitation type, cloud cover, blowing snow, fog. We also use our weather instrument that measures standard meteorological variables such as temperature, humidity, pressure, but we also have our two more sophisticated instruments, laser optical desometer measuring particle size and fall speed, and our MRR measuring reflectivity and Doppler velocity, from which we can derive the melting and the refreezing of particles. We also, during these special events, collect particles on a black pad that you see here, insert it below a camera and take macro photographies of particles to have more information on the formation processes. So we take 9 photography of different area of this pad at every 10 minutes. So these are... So these photography are then analyzed by our algorithm. So we identified all the particles automatically, and they are also measured automatically. But we then sort them in different categories using 4 ice pellet categories that were observed by Gibson and Stewart in 2007. So for our analysis, I will present now. We have refrozen wet snow. These are ice pellets on which remain some characteristic of snow. So for example, here you see that it was a dendrite, and now it melted partially and refroze. This was probably an aggregate with needles, and we still see some characteristic of this snow, and it's why we classified these 2 particles in refrozen wet snow. Irregular particles that cannot be classified in the other categories, then bulge particles, spicules, fractured particles, nearly spherical and spherical particles. So we've associated the 4 ice pellet events with a different condition all left. So 3 of these events were associated with cold warm nose. So the warm nose here for these 3 events is slightly below 0. It's probably a cold bias in ERA 5 data that this temperature profile. However, our MR2 on the rooftop of UQAM on our station measured each time melting there. So it means that in reality, the temperature profile was a bit above 0. But because of this relatively cold warm nose, we've associated these 3 events to partial melting all left. So the first formation process of ice pellet. A fourth event that was associated with relatively warm temperature all left was associated to complete melting and documented in the paper here. And what we see is that the melting is occurring at higher altitude and the refreezing is occurring at low altitude, and at temperature, the refreezing here. So we see a decrease in reflectivity measured by the MR, and it's occurring at temperature between -5 and -10. So we can compare the distribution of different categories of ice pellet during all these 4 events. So we have the 3 partial melting event here and the complete melting event here. So we already see that there is a difference between these 2 types, these 2 processes. So the complete melting event has fractured particles that were not found on pictures taken during the other events. It's interesting. We can look at these different distribution with on a size axis. So it's what I show here. So this is the major axis of the particles that were photographed during the events, with the fraction of different types of ice pellet. So, for example, for this first event here, we see that smaller particles tend to be more spherical or nearly spherical, and larger particles were mostly irregular. And this is the same for the two other partial melting events. So smaller particles are more circular or more spheric, and larger one or can be refrozen wet snow or irregular particles. Because the melting rate of these larger particles is lower, and there is no characteristic that remain even after the refreezing. For the complete melting event, it's completely different. So larger particles seems to be more bulge particles, because the inner pressure of larger particles refreezing is higher, so it tends to form a bulge. And moreover, we have all our fractured particles that are on all sizes, because these fragments can be tiny fragments or larger fragments. It's not very important. And when comparing these different distribution of categories with the fall speed measure, we again found interesting things. So we can take again our first partial melting event. So here what I show is the fall speed as a function of diameters that was measured by the laser optical disturbator during these events. So we see that, and it's compared with rain that was also measured. So in green, the green square here are measurements of rain. The pink squares are measurements of ice pellets. So we see that the green square follow quite well the theoretical curve for rain, and ice pellet, it follow well the theoretical curve for ice pellet until particle gets bigger, and are more irregular, and then these particles are a bit less dense and fall at lower speed. For complete melting event, it's a bit the opposite. So smaller particles contained more fragments, and these fragments have more air resistance because they're less dense and fall at lower speed. However, larger particles, they tend to converge toward the theoretical curve. And the presence of these fragments is explained by the faster refreezing of these particles that occurred between temperature of -5 and -10, and produce more secondarized, more fragments, because the pressure built more fast inside the raindrops. So we can do the same with the two other partial melting event. These two partial melting events contain more refrozen wet snow, because the melting rate all left was lower. So we see that the observation of fall speed diverges a lot from the theoretical curve for ice pellet. However, it would still have been an event that would have been associated to ice pellets by any observation or observational staff. For a large particle, we even see that fall speed tend to get lower a bit, and that's because particles are less and less dense as they get bigger, because their melting rate is smaller. Okay, interestingly, during these 4 events, we also measured slow falling ice pellets. So these are time series measured by the laser optical disturbator of fall speed. So we see that most particles fall at speed here ranging between 3 and 5 meters per second. But as soon as ice pellets are observed, we see these counts here at fall speed between 1 and 2 meters per second. And we observed this second peak for all the event. And we were curious about what was explaining this. And we took a slow motion video of the disturbator, and ice pellet or bouncing particles. So here, if you can see well, maybe it's lagging a bit, but during all these events, we always observed particle bouncing on the top of the disturbator. And when we analyze this slow motion video, and like for a few particles, we realized that the fall speed was almost exactly the same that were measured during each event. So this reminds us that we often need to stay on the field and look at our instruments to know what they measure. So that concludes the first part of my research. So we've associated different, we realized that the laser optical of this drometer was able to measure interesting characteristic about the formation processes of ice pellets. Okay, so the event associated to complete melting was studied a bit more because it was a long duration event and also an event for which it had been forecasted a lot of freezing rain, but finally we observed a lot of ice pellet. So it was documented in this paper here. So we had 10 hours of consecutive hours of ice pellet observation, an accumulation of 18 millimeter of ice pellet in SWE. And this event was associated to complete melting aloft during around 8 hours. Moreover, there were tiny ice crystals on the photographs. So you can see a lot there stuck with the ice pellets. So I'll come back to that. The refreezing was measured at around 500 meters during all the events. So this is a time series of differential reflectivity measured by a radar nearby Montreal. So we see that as soon as ice pellets are being observed at around 4:30, this signature here close to the surface is started to appear on the graph. And it doesn't change height, even though temperature refreezes, it remains always at the same altitude. When we analyze the photographs, we realize that by the beginning of the occurrence of ice pellet, there are some ice crystals hidden in the pictures. And at some point, there were a lot of these small crystals. So this photograph gave us the opportunity to measure the characteristics of these small ice crystals. So this is what's done here. So you have the major axis and minor axis, and all ice crystal measured on photographs are represented. So in average, they were 100 microns per 200 microns, these tiny ice crystals. So, and we know that their fall speed is quite slow. So from theoretical fall speed from this type of ice crystals and the comparison between ice pellets and ice crystals on photographs, we could do a rough estimation of their number concentration, the lower atmosphere. So we arrived to characteristic ice fog numbers between 10,000 and 100,000 particles per meter square, and benchmark model evaluation by using them, we found out that this was enough ice crystals to refreeze all the supercooled raindrops by contact freezing. So this suggested that it was a possibility that supercooled raindrops during that event had been refrozen by contact freezing with ice crystals. Moreover, we tried to understand how these ice crystals could have remained in the sub-freezing layer. So first, we've noted the presence of riming on a lot of ice pellets. So Hallett-Mossop process might have created secondary ice on which could have grown columns, ice crystals. Also, we know that freezing drops produce fragments from our previous study and from the literature. So the nucleus on which these columns could have grown were probably explained by secondary ice production. But how can ice first enter the sub-freezing layer, because it's isolated by the melting layer all left? Well, by doing air parcel trajectories, we found out that there are So this is a representation of precipitation type simulated during the event. So we have rain here in green, in pink in the middle we have Montreal, in pink we have freezing rain, and snow in blue here. So doing trajectory, we find out that air parcel arriving at below 600 meters, where we measured the refreezing during the event, were coming from a region characterized by snow that you see here. So we ended up this study by suggesting that the refreezing of supercool raindrops below the melting layer was maybe triggered by snow entering from the north area of this melting layer and propagating below the melting layer by secondary ice production. So the glaciation was triggered by advection of ice at the beginning of it. And we believe that this process can reduce the area characterized by freezing rain and increase the area characterized by ice pellets if the temperature is small enough to produce enough secondary snow when particles refreeze. And finally, the last part of my work is to try to see if this process that was observed and documented here could be reproduced in 3D simulations using atmospheric models. So for this, we've used P3 microphysical scheme developed by Morrison and Milbron 2015. So this microphysical scheme has two liquid category, cloud and rain with two moments, and has ice category with two moments as well, but for prognostic variables that also include rhyming mass and rhyming volume. So they describe the rhyming in their microphysical scheme as free because rhyming increases on particles as particles enter in collision with cloud particles and rain particles. Recently, Melissa Chalette from Environment Canada also implemented liquid fraction. So it's a fifth prognostic variables, and it allows to simulate the refreezing of ice pellet from partial melting process. So now the question is, can we also add another something interesting about the P3 microphysical scheme is that we can add as many ice categories as we want. So now that we observed very different ice categories, so tiny columnar crystals and bigger ice pellets, could we represent these two types of ice at the same time in an atmospheric model? So this is why we chose this model. So we've done a few implementation in P3. So first, we've added a new secondary ice production. So it already contains a default Hallett Mossop secondary ice production process that's activated just when we have large ice particles with diameter above 4 millimeters. But we've added fragmentation freezing of raindrops that we know during ice pellet event is probably dominating the secondary ice production. So we've used for this parameterization given in Lawson et al., where the number of secondary ice is proportional to the volume of a drop. There's also another parameterization that was used that is given in paper here from Pellets 2018 that was also compared with Lawson parameterization, but I won't show this today. Another change we had to do in P3 is represent better how columns can collect big raindrops. So initially, the collision between big supercool raindrops and small ice crystals was resulting in rhyming all the ice crystals and leaving no columns. But now if the number of supercool raindrops is lower than the number of ice crystals, there will be surviving ice crystals that will be able to nucleate other supercool raindrops in a future time step. So the simulation we've done, I've used the global environmental model, GEM from Environment Canada, and this domain here with Montreal in the middle. We've used an horizontal resolution of 1 kilometer and driven this simulation with ERA5. We also used 2 ice categories, and our goal was to produce a smaller ice categories and a larger ice categories. We've also deleted the immersion freezing using big 53 parameterization to see if our glaciation induced by the snowy region, like showed in the conceptual model, was something that was at the origin of ice pellets and ice crystals. So this is the control simulation. So we see that there are no ice pellets at all in the region between snow and rain, because there is no process in the model that can refreeze the raindrops below the melting layer. So what we have is freezing rain. When we add secondary ice production by Hallett-Mossop by default, it produced some patches of ice pellets. So this is good. So it's probably because in these areas that are characterized by heavy precipitation rates, there are graupel that survive the melting layer and that can produce secondary ice below the melting layer and produce ice pellets. Once we modified the model, we can see that there's a larger region of ice pellet that develops here and that almost reached Montreal. So that's good news for us. It means that we can produce the right precipitation types, that the one that was observed in Montreal during this event. Also, I want to show that how we modified our columns collects supercool raindrops allowed us to better represent the size distribution of particles. So here what I plot is the size distribution of at 100 grid point in the ice pellet region on the map here, so in the red square. And for the 2 categories, so the second categories is in orange, the first categories is in blue, and the black dots and bars are the observations that we've done during during the event. So we see that there are more or less a good agreement between the modelization and the observation. So ice pellet with a densitometer and ice crystals with the photography, also taking account the fall speed, theoretical fall speed of ice crystals. When we don't apply our modification, we don't find that good agreement between the size distribution and the observation. And finally, we have cross sections going from the north of Montreal to the south of Montreal. And we kind of see, as it was shown in our conceptual model, that the ice seems to infiltrate the subfreezing layer by the north side and gently descend towards a region to the south. So this is Montreal in that case. So in our event, it seems that the ice pellet region reaches Montreal. This shows the riming. So we have a category with heavy rimed ice. So this would be ice pellet that are theoretically 100% rimed, and another category that is less rimed that would be associated with ice crystals. So that third part showed that we could simulate ice pellets and ice crystals at the same time with realistic size distribution, and that rain immersion freezing is not necessary to produce ice pellets during this event, because we have these 2 types of particles that interact together and produce the type of precipitation that we observed. So that concludes what I wanted to present to you today. So there are kind of three parts to my PhD research. So the first one is how we can measure ice pellet characteristic and even formation process with a laser optical desonator that is used in different field campaigns and research. And that first part was really useful to complete the other parts of my PhD, and will be useful to analyze other data collected during different field campaigns in which I participated. Then we found out that secondary ice production and ice advection were playing a key role in increasing in area affected by ice pellets, and at the same time reducing the area affected by freezing rain. And finally, we were able to implement these different processes to produce ice pellets and ice crystal more realistically in an atmospheric model. So with that, I'd like to thank you again for listening, and I'm hoping to answer your questions.